Hello everyone and welcome to our calculus notes for section 3.4. Our first topic we're going to discuss is something called concavity. We're going to let a function be differentiable on an open interval I, and we're going to say the graph of f is concave upward on I if f prime is increasing on the interval. So concave upward, you've dealt with this before in dealing with something like a parabola. It would look something like this. So on the interval that I've drawn, this thing is concave upward. And what you've learned before is that this graph opens up. So graphically we can see that it opens up. What we want to do is talk about this a little more analytically in terms of the derivative. Now what's happening here, if a graph is concave up on an interval, the derivative is continuously increasing on that interval. Okay, so we could just take a couple points right here and let's talk about the derivative of the function at each of these points. Now we know the derivative is the slope of the tangent line. Okay, so we're going to draw some tangent lines here. Okay, now this one, that's fairly steep and negative. If we were to draw the tangent line through this point, notice here that it is still negative, but it's not quite as steep. So we would say that this derivative at this point is larger, or has a higher value, than this derivative right here. Now if we look right here, this is our minimum, and we knew that the derivative is 0, so we have our horizontal tangent line. So 0 is larger than a negative number. So you can see so far our derivative is increasing. The derivative at this point is the slope of this tangent line right here. And we can see now that this tangent line is positive, which is larger than 0, so the derivative is still increasing. And then if we look at the derivative here, we get this tangent line. And you can see that this graph is steeper than this graph, so therefore this one has a higher slope, meaning the derivative is still increasing on that entire interval. Now one thing to notice is the graph lies above all of its tangent lines on the interval. So you can see here these tangent lines are all below the graph, and the graph is above all those tangent lines. What we're going to learn today is the way we're going to be able to find this is that the second derivative is going to be positive for all the x's on the interval. So we think about this as if the derivative is continuously increasing, well, the second derivative tells us what the first derivative is doing. And so if the second derivative is positive, that means that the first derivative is increasing. Okay, so that's kind of the idea of what's going on here. Concave downwards is the same type of idea, except now our graph is opening down. Okay, so visually that's what it looks like, and our derivative is constantly decreasing. So we could pick some points on our interval again, and to really view the derivative we could see our tangent line here. Okay, so that's very steep, positive, still positive, not quite as steep. Here we would get 0. Here it's negative. Okay, and here it's very steep and negative. So you can see that our derivative was a very high positive number, a little bit lower to 0 to negative to very low negative number. And so you can see that the derivative, f prime, is decreasing on the interval. So what happens here is the graph is going to lie below all of its tangent lines. So you can see here that the graph is completely underneath all the tangent lines. And it turns out now that the second derivative is negative for all the x's on the interval. So in our first example, it says determine the open intervals on which the graph of f is concave upward or downward. Now we can look at this graphically, and you can see here we kind of have this sloping down and then this curving up here. And so we might assume that it's concave down on this interval and concave up on this interval. What will always work to determine whether something is concave up or concave down is using the second derivative to determine the concavity. So what we want to do is locate the x values for which f double prime of x equals 0 or does not exist. Okay, we're going to use these x values as our testing intervals. And then we want to test the sign of f double prime of x, or the second derivative, in each of the testing intervals. Now we also want to use x values where f is not continuous or f prime does not exist. First off, we need to find that second derivative. We have to find our first derivative. That's just 3x squared plus 3. And then we go ahead and find our second derivative by taking the derivative of the first. So power rule, we get 6x and then plus 0. So we found our second derivative, and what we want to do is find where the second derivative equals 0 or does not exist. You can see it exists on the whole number line, so we don't need to worry about that. And we can see that it equals 0 when x equals 0. So 0 really becomes our marker here for our concavity tests. We're going to put 0 right here. So we're going to have an interval to the left of this, which will be negative infinity to 0. And then on the right of this, it'll be 0 to infinity. All right. So next we want to pick test values that fit in this interval. So I'm just going to try f double prime of -1 here. And here we can try f double prime of 1. So keep it simple. It just has to fall in the interval. So if we were to plug -1 into our second derivative here, we would get 6 times -1, which is -6. And what we're interested in is the sign of f double prime of x. And the sign is negative. Okay. For this one, f double prime of 1, so we're going to plug 1 into our second derivative. So 6 times 1 is 6. And what we're concerned about is the sign. And this is positive. So the conclusion is, if the second derivative is negative on an interval, we call this concave down. And if the second derivative is positive on an interval, we call this concave up. So what this means is, if the second derivative is negative, it means the first derivative is always decreasing on this interval. And if the second derivative is positive, the first derivative is increasing on this interval. So we get concave down and concave up. Our concave down interval would be negative infinity and 0, and we write it as an open interval. And then it's going to be concave up from 0 to infinity. So in our graph, we would see here that this all is concave down. And we can see here that's true because f double prime of x is less than 0 here. And then on this interval, from 0 to positive infinity, we can see it's concave up because f double prime of x is greater than 0, or it's positive. All right, we're going to move on to our next example here. And I want you to try this one on your own. Welcome back. So hopefully you're able to find your first derivative. Okay, and then move on to your second derivative. Here you had used the quotient rule. And it gets a little bit messy, so to clean these up, we factored out some stuff, and we come out to something like this. Okay, so if you're still struggling with how to find those first derivatives or second derivatives, please come see me for some extra help. Then the new stuff today was applying, just setting the second derivative equal to 0, so that would be where the numerator equals 0, and then we can see here that we get x equals 1 or -1. Now those guys end up being our testing intervals here at -1 and 1. And so you can see we picked the intervals right here. We picked test values. In those intervals, your test values may be different, but the signs of the second derivative is what we're really concerned about. And so you should have gotten concave up on the interval negative infinity to 1, concave down on negative 1 to 1, and concave up from 1 to infinity. And we can see here on the graph that the first derivative is increasing all along this interval. And then we can see the first derivative is decreasing on this interval. And then the first derivative is increasing on this interval. So we can see concave up, concave down to concave up. So that has been how to find concavity of a function on an interval. Our next topic is called points of inflection. So a point of inflection is the point where a function changes concavity. So the concavity either switches concave up to concave down or concave down to concave up. So we're going to draw a couple examples of points of inflection. In our first graph we have concave up and then it switches to concave down right at this point right here. So that would be your point of inflection. So we had concave up to concave down. Okay. Another example. Here we have concave down, and then it switches to concave up. So here would be your point of inflection. Here was concave down, and here was concave up. Another example here. Okay, so the point of inflection will be right here where we switch from concave up to concave down. Now one thing you're going to want to notice here is that if we drew the tangent line at the point of inflection, the graph crosses over from one side to the other side at that point of inflection. Okay, and we can see that that's true here, and it's true here as well. Now, if f of c is a point of inflection, then either f double prime of c equals 0, or f is not differentiable at x equals c. So here's what we mean by that. So if this was our c right here, we would know that f double prime either equals 0 or does not exist at these points. Okay, so here and right here. Let's look back at some of our other examples because we were dealing with concavity. So let's go back and we'll look at this one. So remember, a point of inflection is where we switch from concave up to concave down or concave down to concave up. So in this graph right here, it's where we switch from concave up to concave down. So this would be a point of inflection right here, and our c value would be -1. Now you can see at -1 what was happening to our second derivative was our second derivative equaled 0. And we see there was another point of inflection here because we switched from concave down to concave up. So that's also a point of inflection. And we can see that the second derivative was also 0. So always two things that have to happen. The second derivative has to be 0 or not exist, and we have to switch from concave up to concave down, or concave down to concave up. Alright, so we're going to try this first one together here. It says determine the points of inflection and discuss the concavity. So they really go hand in hand. So again, we need to find our second derivative. So our first derivative is 4x cubed minus 12x squared. And then our second derivative is 12x squared minus 24x. So we need to find where this does not exist or it equals 0. Well, it's going to exist everywhere, so we'll just set this equal to 0. And we can take out a 12, so we're left with x squared minus 2x. and we can factor out an x. We're left with x minus 2. And so our second derivative equals 0 when x equals 0 or 2. So can we automatically say that a point of inflection happens at x equals 0? No, because we have to make sure and test the concavity to see that it actually switches at these x values. So we still have to find our whole concavity here. So we have our interval, negative infinity to 0, and 0 to 2, and 2 to infinity. We'll pick some test values here. Let's try negative 1. So negative 1 squared is positive, times 12 is 12, minus 24 times negative 1, so that's plus 24, and so that is 36. We get a positive second derivative, so the conclusion is concave up. This interval, we could try 1, so let's try f double prime of 1, and we're going to get 1 squared is 1 times 12, so 12 minus 24 times 1, we get negative 12 here. And so the second derivative is negative. We say this is concave down. And here, let's just try 3. So we get 3 squared is 9. 12 times 9 is 108. Minus 24 times 3, which is 72. 108 minus 72 is 36. So we can see that that's going to be positive, and so we get concave up. Okay, so our possible points of inflection are right here at 0 and then at 2. And what makes them points of inflection is if it switches from concave up to concave down at that point. And you can see that it does here. So here we had concave up on that interval, and then here we had concave down on this interval, and then here it switches back to concave up. So because that happens, we actually get a point of inflection at 0, comma, whatever the y value is, and at 2, comma, whatever that y value is. So if we just plug this back into our function, 0 to the 4th minus 4 times 0 cubed, that equals 0. And if we plug 2 in, okay, we'll get 2 to the 4th minus 4 times 2 cubed, and that is negative 16. So we do get our 2 points of inflection right here. All right, let's try our next example. Here we have x to the 4th, and if we want to determine the points of inflection, we would go, let's see, f prime of x is 4x cubed. Then we'd get f double prime of x, which is 12x squared. We set that equal to 0. And so x equals 0. So the point that is a possible point of inflection is here at 0. Graphically, it looks like this is going to be concave up and then concave up. So it doesn't switch. But let's go ahead and test out this interval, negative infinity to 0 and 0 to infinity. So here we can just try negative 1, so f double prime of negative 1. Here we get, so that becomes positive 1, that becomes 12, which is positive, meaning this is concave up. And then let's try f double prime of 1. So that's going to be 1 squared times 12, that's also 12, also positive, so we get concave up. So if we had concave up to concave up, this is not a point of inflection, because the concavity did not switch at 0. Alright, so that is how to determine points of inflection of a function. Our next topic is going to involve something called the second derivative test. And what we're going to be doing is finding another way to determine if a point is a relative minimum or a relative maximum. What we're going to have is a function where f prime of c equals 0. And we'll recall that that is where our critical numbers happen. And the second derivative of f exists on an open interval containing c. And we're just saying if f double prime at that critical number is greater than 0, then f of c is a relative minimum. And if f double prime at that critical number is less than 0, then f of c is a relative maximum. So what we're going to do is find the critical numbers of the first derivative, and then plug those critical numbers into f double prime of x, and that's your second derivative test. So if f double prime is greater than 0, then it's a minimum. If f double prime is less than 0, then it's a maximum. Now it could happen that f double prime equals 0 at that critical number, and so our second derivative test would fail here. In this case, you would have to revert back to our first derivative test. Okay, so let's try it here. It says find the relative extrema for the function. So the first thing we need to do is find the critical numbers of f prime of x. So let's find our first derivative. We get negative 15 x to the fourth plus 15x squared. And we want to see where this equals 0. So we can take our negative 15 out of all this, and we'll be left with x to the fourth minus x squared. So now let's go ahead and take out a common factor of x squared, and we're left with x squared minus 1. And so looking at this, we can see that x is going to equal 0, negative 1, and 1. So these are our critical numbers. Okay, so what we have now is the critical numbers x equals negative 1, x equals 0, and x equals 1. And these are possible relative extrema happening at these points. So we want to actually plug these in to our f double prime. So here we want f double prime of negative 1. And so what we need to do is find that second derivative. So f double prime is going to equal negative 60 x to the third plus 30x. Okay, so now plugging negative 1 in here. Okay, so negative 1 cubed is still negative 1 times negative 60 is positive 60. Plus 30 times negative 1, well, that's negative 30. So 60 minus 30 equals 30. If we find f double prime of 0, well, that's going to end up equaling 0. And then f double prime of 1, so that's going to be negative 60 plus 30 is negative 30. So we plugged our critical numbers now into our second derivative, and let's go ahead and get the signs here. So here this is positive. Well, here it's 0, so it's neither positive nor negative. And here this one is negative. And let's come up with our conclusion. Let's apply that second derivative test. It says if f double prime is greater than 0, then it's a minimum. So greater than 0 and positive are the same things. So this one right here is a minimum value. If it equals 0, this is a fail. Okay, so this one fails the second derivative test, and it's going to tell us to use the first derivative test. So let's get to that in a second. And then here, this one is negative, meaning f double prime is less than 0, so we call this a maximum. Okay, so here we get a minimum at x equals negative 1. So we need to find the y value here. So we can plug negative 1 back into this equation. So this becomes positive 3 minus 5, and we get negative 2. This one failed. We'll look at that in a second. And then we get a maximum at 1, comma. Well, we'll plug 1 into our function. So this is negative 3 plus 5, which is 2. So we know we have a relative min at negative 1, negative 2. And graphically, we can see that that's true. And then we have a relative maximum at 1, comma 2. And graphically, we can see that that's a maximum as well. So what do we do when the second derivative test fails? Well, we have to move to the first derivative test. So we still use our critical number of 0, and the interval would be from negative 1 to 0, okay, because negative 1 was our other point. And then above 0, it would be 0 to 1, because 1 was our other critical number. So we need test value in here, and we're going to test it into our first derivative. So this is going back to what we did a couple days ago. Let's try f prime of negative 1/2. And where are we going to plug this in? Into the first derivative, because we have to go back to the first derivative test. So we'll plug into our first derivative, which was right here. And go ahead and just type that into your calculator. You're going to come up with 2.8. And then for this interval, let's go ahead and test 1/2. And then you're also going to get 2.8 here. So we need the sign of our first derivative. So that's positive, and here it is also positive. So if we go from an increasing function to an increasing function, okay, it's kind of like going up and then up some more, we do not get any relative extrema. So this one is increasing, and this one is also increasing. So because it's increasing on both sides of this critical number, we have no relative extrema here. Okay, so just shortly recapping what we did. So we wanted to find relative extrema, so we found our critical numbers by finding our first derivative, setting it equal to 0, getting our critical numbers. Then we plugged the critical numbers into our second derivative, so we found our second derivative, and we plugged in each of the critical numbers, and we found the sign for each of those. So if it was positive, then it was a minimum. If it was negative, then it's a maximum. And if it's 0, it failed, and we had to revert back to our first derivative test. So we came up with our intervals around that critical number that failed the second derivative test. And in the first derivative test, we got positive on both sides, so it was increasing, meaning no relative extrema. All right, so that is how you can find relative extrema using the second derivative test.